Okay, hey guys, we are going to do this practice exam 4. This is the topic list. It should be on the first page of that poster practice exam. And then we have all the information that you're going to need. At the top it says any KAs will be given to you. So if we come across something where you need a KA, that will be given to you. There's also these additional equations. There's one that I realized I missed, and that is, let me get a better pen here. That is pH plus POH equals 14. So that one will also be on there. But these are the equations you'll get. You'll also get this solubility chart. So I think that's about everything that you'll need for the exam. Okay, let's go ahead and get started in doing this. I'm going to do it with you every step of the way, including the calculations. So let's start with gas laws. So it says a balloon is filled with 36.2 grams of N2. The only time we keep stuff in grams is if we got that weight per volume percent. Otherwise, we always turn it to moles. So step number 1 is we're going to turn this to moles. So we take that, divide it by the 28.01 grams per mole. So I'm going to take 36.2 divided by 28.01. And I get 1.2924 mole. Now, I always calculate the sig figs. It should have just 3 because that had 3 and that had 4, but I keep 2 extras for future calculations, or use what's already in your calculator. All right, now I can read the rest of the question. It says at STP. Do you remember what STP is? That's standard temperature and pressure. So at STP, the temperature is 273.15 Kelvin, and that would actually have infinite number of sig figs. The pressure is 1.00 atm, and you were just asked to memorize that in our lecture class. We know the moles, by the way, is 1.2924 mole with 3 sig figs, and now it's asking for the volume of the balloon. All right, so it didn't have anything that changed. There's no initial pressure and final pressure, no change in temperature. So we're safe to assume we got pressure, temperature, moles. We're looking at the gas law. Remember PV equals nRT. And just to do some algebra before we start plugging numbers in, we're solving for V. So V, in order to get V alone, you divide both sides by P, right? And that cancels them out. So now we have the equation V equals nRT over P. And we just start plugging things in. Our N is at 1.2924 mole. Our R is 0.0821 liters ATM over mole. Okay, if you didn't know that, you could go back to the very first page, or second page rather, where you're given the actual R. So, or you could memorize it because you've worked with it so much. And then T is 273.15 Kelvin. And we're going to divide all of that by the pressure, which was 1.00 atm. Remember, all the units need to be in liters. Volume is liters, pressure is atm, grams need to be turned into moles, and K is our temperature that we need this in. Okay. So I'm going to take the answer that I already have in my calculator, times 0.0821 times 273.15, and then divide by 1, which would give us the same answer. And the answer I end up getting is 28.98 liters, but again, remember it had 3 sig figs, that had 3, that had 3. We said at STP this stuff has infinite, so we're looking for 3. So 28.98 is the same as 29.0 liters with 3 sig figs. All right, moving on to the next one. It says a container with 785 torr contains 41% carbon and 59% gas by volume. I like just changing things immediately into ATM because, again, the gas constant's in ATM, so that's what we should be looking for. So I'm going to take 785 torr and divide it by 760 torr per ATM. So 785 divided by 760 gives me an answer of 1.03 with 3 sig figs, and then I keep those 2 extra sig figs, 29. And that again is in ATM. All right, so essentially it's saying, hey, you've got this container. About 41% of it is CO2. And then 59% is O2. And it's asking for the partial pressure of oxygen gas. That's that P with the O2. Now, do you remember that to find a percent of anything, you put it into a decimal percent and then multiply it by the thing you're interested in? Well, what this is saying is that the total pressure of this whole thing is that 1.0329 atm. But we're only interested in 59% of the pressure because 59% of it makes that up. So how we do that is we move the decimal place 2 times, 1, 2, to get a decimal percent, and then we multiply it by the respective total pressure. So I'm going to multiply this times 0.59, and I get an answer of 0.609 ATM. And again, it would have 3 sig figs because this one originally had 3. Actually, I'm lying to you. This has only 2. This has 3. So our final answer should have 2. I'm going to say 0.61 ATM, unless otherwise assumed. If they tell you a percent, then you can assume it's a, unless otherwise told. If they tell you a percent, you can assume the number of sig figs. So 0.61 ATM. All right, double displacement reaction of sodium chloride and lead nitrate. I did you just a disservice here because lead nitrate doesn't actually exist. It should be sodium chloride and lead 2 nitrate. It won't affect the actual answer here, but if we're asking you to balance a reaction, that would be a pretty imperative part. Okay, so double displacement. Do you remember that? That's where you take the anions and you switch them. Voot, voot. So the chloride and the nitrate are going to switch, and you get sodium nitrate and lead 2 chloride. So essentially, if this reacts with that, you would make, these would be your products, that and that. All right, and it wants to know that which of these would be a solid, if any, because maybe the multiple choice says there's might not be one. Well, sodium nitrate is NaNO3, and lead 2 chloride is PbCl2. Remember, sodium's got a 1+ charge, nitrate's got a -1. If lead has a 2+ charge, which it does in lead 2, you need 2 chlorides to cancel that out. So now we go over to our solubility chart. All right, and it says anything with a sodium or anything with a nitrate will always be soluble. So you got sodium and nitrate. In other words, that's saying that's going to be aqueous. It's going to be dissolved in the solution. Let's look at lead 2 chloride. We find chloride and see that it's generally soluble, meaning it will generally be aqueous. But when it's paired with silver, mercury 1 is what that's called, or lead 2, the results are insoluble. So that means this is going to be the solid, and your answer would be PbCl2. All right, molarity example. So it says when you've got this many mole of calcium chloride dissolved in this many milliliters. Again, anytime we're not working with the weight by volume or volume by volume percent, we're going to turn this stuff into liters. So this would be 0.535 liters. Just move the decimal place 3 times. And it wants to know the exact, the resulting concentration in big M. Big M is mole over liters. So our question becomes relatively straightforward. Do we know the mole and do we know the liters? Yes, we know the mole. It's 3.16 mole. Do we know the liters? Yes, we do. 0.535 liters. And that's the only way you get resulting units of mole over liter. Remember, big M is equal to mole over liter. So 3.16. 3.16 divided by 0.535 gives me an answer of 0.535 5.91 mole per liter. Cool. All right, so that would be the answer for that one. Now we can move on to the next part. Let me grab a fresh sheet of paper here. We're talking about dilutions. So anytime you see the word dilute, dilutions, etc., diluted to, you're going to immediately think of the equation C1V1 equals C2V2, where the C's are the concentrations and the V's are the volumes. And they can be in anything. You can be in part per million, volume over volume, weight over volume, even molarity. And then the volume can be in anything as long as it's the same on both sides. Liters, milliliters, quarts, cups, it really doesn't matter. Hats, weird ratios, it doesn't matter as long as they're the same on both sides. Okay, so this is saying you've got this container of lemonade. So imagine you've got some yummy, delicious lemonade. And it says you got 1.2 liters of it. It's saying right now the concentration is 4.2% sugar. And it says, hey, what volume do you need to fill it to in order to have the concentration actually be 3.5%? So you don't need a whole lot of filling to get from 4.2 to 3.5, you know, you just want to fill it a little bit. But let's go ahead and see if we can figure it out. We're looking for initial concentration and initial volume. Well, our initial concentration is this 4.2, and our initial volume is where we originally started, that one. Our final concentration is this 3.5, and our final volume is what we're looking for. That's our V2. So let's go ahead and plug them into this equation. C1V1 equals C2V2. Because we're looking for our final volume, we know that already, we can move this C2, divide each side by C2 right away to get that V2 alone. So now our equation is C1V1 over C2, and that would all be equal to V2. So we can plug in our C1, that's our 4.2%, and that's weight by volume percent. I do like to write the units just because they cancel out, and I like to see that. Our initial volume is 1.2 liters. And we're putting all of this business over our final concentration, which is that 3.5 weight by volume percent. The reason I like to do that is that this weight by volume and this weight by volume cancel, because you've got something divided by the same one, so they're going to cancel. The only units left is liters, and that's good because we were looking for volume. So the way I would input this, I've got 4.2 times 1.2 divided by 3.5. I get an answer of 1.44 liters. This all would have two sig figs, so I'm looking at 1.4 liters. And that should make sense. We know that the number has to be higher than 1.2, and it wasn't going to be hugely higher, so 1.4 liters is what we'd have to fill this sugary stuff to get a 3.5% concentration. All right, now we're in weak acids, weak base reactions. We should know our strong acids. I'm not going to go write them right now because they're elsewhere and written many times. But if it's not a strong acid and it starts with an H and it's aqueous, chances are it's going to be a weak acid. So it says balance the reaction of HF and NH3. The difference between weak and strong acids is weak acids are going to have a double arrow. Remember, strong acids completely dissociate. So there's a strong arrow going one single direction. That's what makes them strong, is that they break apart completely. But here, when you have a weak acid like HF, which is not in our strong list, our strong acid list, it's not going to break apart fully. So you get this two-way arrow. All right, so remember what we're looking at is this is the acid. It's going to give off this H+, and that H+ is going to go over here to this dude. And what you're going to be left with, once this goes over there, you'll have NH4+. And then the resulting thing will have to be negative because you took away a positive. All right, so this is the balanced reaction. One thing I didn't really ask you for, and this is naming stuff, but I probably will. By naming stuff, I mean the terms. So for example, this was the acid. It was this thing that gave off the H. This was the base. Meaning this over here, if this is the acid, this thing without the H is going to be the conjugate base. and this is going to be the conjugate acid. So I might ask you that as well. But in a question like this, I'm looking, do you have the full arrow? Do you have all the charges correct, etc.? All right, now we have a balanced reaction between HCl and calcium hydroxide. HCl is just HCl, I give it to you. And calcium hydroxide, calcium, remember, is in the second column. It's got a 2+ charge, and hydroxide is OH-, so we need 2 of those. So calcium hydroxide is CaOH2. And it's saying react those two things. Well, this is a strong acid. It's on your list of acids to memorize. So we're going to draw a one-way arrow telling you it completely dissociates, completely break apart. And remember, what we make when we have a strong acid and a strong base, anytime you have hydroxide, in fact, in an acid, you're going to make water. This gives off 1H+. But this one has 2 hydroxides, hence that 2 right there. So it's got an OH- and another OH-. So your question becomes, if I got 2 OH- here, how many H+ do I need? Because to remind you, an H+ and an OH- makes 1 water. So we need to put a 2 here to get 2 H+, because we had 2 H-. So you need these numbers to match. For every H+, there's an OH-. That makes a water, that makes a water, and your result is 2 waters. We've used up the H, we've used up the OH. The only thing we didn't leave or use up was a calcium and 2 chlorides. And how convenient is that? Because calcium chloride is CaCl2. Woohoo! All right, last but not least, we have this lovely one where I ask you, I tell you the pH of soda equals 3.9. I ask for the POH, the H3O+, and the OH- concentration. Now remember, if you have one of these 4 variables, you can solve for the other 3 using the equations at the front of the book. Okay, so here are those equations for you. So the first one we're going to use there, although you could solve for POH in a variety of ways. You can first find the H3O+, and then find the OH-, then go back and find the pH or POH. One of the easier ways, I think, is to use this right here, which is why I realized I didn't have it provided. So that's pH plus POH equals 14. In other words, if I were to write this, pH plus POH equals 14. We know that pH is 3.9 plus POH equals 14. What that means is if you subtract 3.9 from both sides, POH can only equal one thing, and that's 10.1. So POH has to be 10.1. Then to find the H3O+ concentration. The H3O+ concentration you can find in a couple different ways, but this is probably the straightforward one because we're trying to link pH and H3O+, and it's with here. And we say it's 10 to the negative pH equals our H3O+ concentration. In other words, 10 to the negative 3.9 will equal our concentration. So how we do that is we say 10, use your little hat, to the negative 3.9, and then enter. I get an answer of 0.00013, which would also be 1.3 times 10 to the negative 4 if we move that decimal place 1, 2, 3, 4 times. And that's mole per liter. That's what the bracket tells you, that it's in units of mole per liter. All right, let's do that same thing for the OH-. It says 10 to the negative POH equals our OH-. So we're just taking 10 to the negative 10.1. And that will equal our OH-. So 10 to the negative 10.1 will give us our OH-. I get 7.9 times 10 to the negative 11. And that would be also, again, in mole per liter. So there you have it. We solved pH, POH, well, pH was given to us, H3O+, and OH-. I hope this helps, and you guys have a wonderful, wonderful study day. Bye.